On the slide, I wrote two things. The first thing is the CH3Br plus OH minus, and it gives you CH3OH plus Br minus. This molecule, when you interact with OH minus, and then people do the experiment and measure the differential rate law, they found out the reaction rate is equal to a rate constant K times the concentration of the CH3Br and the OH minus into the first power. Reaction number 2. CH33Cbr plus OH minus. Formula-wise, they actually look very similar. However, kinetics-wise, the rate only proportional to the first order of your CH33Cbr. Why in the first reactions it's first order to both reactant, and in the second one it's actually only related to the first order of one of the reactant, not both. So when scientists see these reactions, they got very confused in the very beginning. And later on, they realize the reason this is proportional to the first order of both reaction species is because the OH minus need to first encounter the CH3Br so that your Br can leave. They can produce the final product, CH3OH plus Br minus. In this step, the key thing is these two species need to encounter with each other in the right orientation. Then the reaction will happen. In other words, in this specific reaction, the rate determining step is actually how fast these two species can encounter each other in the correct orientation. So things actually involve two species at the same time. That's why you see the first order on both reactants. Use that analogy. Can you explain why for these reactions it only proportional to the CH33Cbr to the first power? Why so? The main differences between these two molecules is this, right? On the top you have CH3. At the bottom is actually you have 3 CH3. So what it does is provide a very strong stereo hindrance. This 3 is actually so big. Under this case, your OH cannot even see the carbon. So that carbon is actually well protected by the 3 CH3 group. So OH minus is not going to be helpful. So later on, what scientists realize is actually this guy need to first undergo a dissociation itself to form this. So that the carbon is actually more open, because right now the bromide leaves, they actually give you more space for the OH to actually attack it. And in this step, this dissociation and to create this species is actually a rate determining step. So once this is formed, your OH can actually hit this one quickly to form the product. And then because this is actually a rate determining step, that's why it is actually a contributor to your rate laws. So this example is just to let you know the rate determining step will be the determining step for your rate laws. Using this concept, how do scientists actually propose a reasonable reaction mechanism? There are actually a few terminology we need to go through first. The first things they create so-called the elementary steps. The rule number 1 is the sum of the elementary steps must give the overall balanced equation. And then the second is actually the mechanism must agree with experimental determined law. Of course, I mean, you propose a mechanism, you need to fit into the data you observe. Okay, so this must be true. And then the good thing about the elementary step is that once you write out the elementary step, you can simply write out the corresponding rate law based on your elementary step. For example, if today you have an elementary step like this, the O3 become O2 plus O. If this is an elementary step, then your rate law will simply equals to a rate constant K times K to the first power, because the coefficient is actually 1. If today the elementary step is like this, O3 plus O3, that give you 3 O2s. So we can write this as 2O3 become 3O2. If that is the case, then you can directly write out the rate law is going to equals to K times A to the second power. And if your reactant species are different, so if it's A plus B, they give you the product, then the rate law will simply equals to K times A times B concentration. One more example. If today your reaction species is like this, 3O2, they give you 2O3. Then basically you have 3 species adding up, they give you a product. Then the rate is just going to equal to your rate constant K times your reactant to the third power. If it's actually 2A plus 1B, then your rate is going to equal to K times A to the second power times B to the first power. In other words, the coefficient for your elementary step is simply the stoichiometry of your reactant. This is only true when you have elementary step. It is not true for your final equation. It's just only true for your elementary step. You can only do this when the question says these are the elementary step. So this is very important because many students mix the concept about the elementary step and the overall reaction equations. So let's give you one example so that you will see how the things is going to work. Here you can see this is the overall balanced equation. And then here you see step 1, 2, 3. These are the 3 elementary steps. So in your homework, you're going to see this quite often. It will give you actually a few elementary steps and then ask you what is the red laws. How are you going to solve this? Okay, there are actually a few things you want to follow. The first thing is to make sure all your elementary steps add up. It must go back to the final balanced equation. First, highlight your reactants. In this case, what is your reactant? So that's your reactant. What is your product? NO2, right? When I see my elementary steps, I will highlight my reactant as well my product. When you add this step 1, 2, 3 together, you need to actually go back to the original equations. So here you can see there are 2 NO3 and then there's 2 NO3. So this is going to cancel out when you add up. And then NO is going to cancel out when you add it up. When you add it up, you can see there are 2, 3, 4, 5 on the right hand side, and on the left hand side there's 1, right? When you add them all up, on the left hand side you have 2 and 2, O5. On the right hand side you have 4 and O2 plus O2. So the first step you do, make sure when you add it up, this go back to the original equation. Many times when they give you this type of questions, they actually don't give you this coefficient. Then if they don't give you that coefficients, when you add it up, it did not actually go back to the original equation. Then to actually plug in some coefficients so that when you add up all your elementary steps, it gives you back to the original balanced equation. Okay, so assuming we can do this first step without any problems, the second step is write down what is your reactants, which we know is actually N2O5. What is your product, which we know is actually NO2 plus O2. All the things that cancels out when you add up your elementary step, we call them intermediate. So in this case, your intermediate will be NO3 and NO. The next thing is actually you want to derive your red laws from your elementary step. So we know the red law ultimately is determined by the slowest step among your elementary steps. In other words, step 2 will be your slowest step. So what you can do is actually you just write out the red law. The red law is going to equal to a rate constant K times the reactant species, right? In this case, it's actually NO2 concentration to the first power, NO3 concentration to the first power. However, we know when you have these equations, from the things we learned, we know the final rate law is going to equals to your K, let's say the final rate constant, times your reactant species actually N2O5 to certain power. When you look at this two, you realize none of this is actually your reactants. So what you need to do is actually to substitute this species. So how do you do this? The way you do this typically through the equilibrium constant. So if you look at the first elementary steps, you can write out your equilibrium constant, capital K. K1 is going to equals to NO2 to the second power, NO3 to the second power divided by your N2O5 to the second power. I can move my N2O5 to the left, and then take the square root of this, then I know my NO2 concentration times NO3 concentration is going to equals to the square root of equilibrium K1 times N2O5 to the first power. Then you will realize this is just this. So you can actually substitute these guys with these terms. So your rate can be rewritten as K times the square root of K1 times N2O5 to the first power. And this combination of these constants is actually your Kf times N2O5 to the first power. So up to this point, you know your rate law is equals to rate constant Kf times your N2O5 to the first power, so that you know the N here is going to equals to 1. So it's actually very simple, right? First, make sure that all the elementary steps, when they add up, they give you the final balanced equation. Second step, identify the reactant, product, and intermediate. Third step, write out the rate law based on the rate determined step. And check out the species here. If it is not the same as your reactant species, you need to use equilibrium constants to do some substitutions. So eventually, the rate law you have, this species is actually belongs to your reactant. Those are the 4 steps that you need to pay attention to finalize and determine the rate law based on your elementary steps. So a gas phase decomposition of N2O is believed to occur about 2 elementary steps, step number 1 and the step number 2. And they say experimentally the rate law is found to be rate is equal to K times N2O5 to the first power. So the first thing you need to do is actually write down the equation for the overall reaction. Okay, so if you write these things down, we know O and O is going to cancel out. So on the left-hand side, what I'm going to have is actually 2 N2O5 is going to give you 2 N2 plus O2. No, O5, N2O. So in the beginning, I just added up, right? I didn't actually add in any factors, right? I just added up and see whether it's balanced. If it is, then done. Nothing else I need to do. But if it is not, then I need to actually multiply factors in either your step 1 or step 2 to eliminate the intermediates. You have 4 nitrogen on the left, 4 nitrogen on the right, and then 2 oxygen on the left, 2 oxygen on the right. So it's actually all balanced, right? And then you say experimentally the rate law is found to be rate is equal to K times N2O to the first power. That's actually the first question, right? Write down the equation of overall reaction. We know this is actually the overall equation and it's actually balanced already. There's nothing else we need to do. Identify the intermediates. So what is the intermediate? It's actually the things that cancels out, right? So you know the intermediate is actually just O. What can you say about the relative rates of step 1 and step 2? These are all elementary steps, right? So one of them must be the rate determined step, which we can use to write out the corresponding rate law, right? So let's say, assuming your second step is slow, the rate laws, you know, need to write something like the rate is going to equals to N2O concentration to the first power times O to the first power, right? If the second step is slow, then you know you can just write out the rate law using your elementary step. However, when you write these things out, you realize you know your determined rate law is like this. And then if the second step is actually a rate determined step, you can actually get back to the correct rate laws. In other words, the second step cannot be the slow step. In other words, your first step is actually the slow step. Let's see whether that's actually true or not. Okay, if the first step is actually your rate determined step, then you know you can write out the rate equations is just equals to your K times N2O. So if the first step is actually the rate determined step, then you can actually get the red laws. Let's actually agree with the experimental determining one. And what it tells you is actually the first step has to be your rate determined step. So the first step has to be the slower step compared to the second step. The step 1 is slower than step 2. All right, so let's look at the second example. So under certain conditions, the experimental rate law for the gas phase reaction for the molecular hydrogen with molecular bromine, the reaction is actually like this. So that's the overall balanced equation. And then they say the rate is going to equal to K times H2 times Br to the 1/2 of the power. Show that the unusual half reaction orders of Br2 can be explained by the following mechanism. So remember the 4th step we talked about. The first step is actually when you add up all your elementary steps, you want to get back to your balance equations. So when you add these things up, you'll realize it did not actually get back to this. So what you need to do is actually you need to multiply 3 here. So when you do this, you will end up with plus 2Br2. That's going to give you 4HBr. You can see it's not exactly the same, but if you divide the coefficient by 2, then it actually gets back to the original balanced equation. So that's actually the first step that you need to do here. And the second thing is to write down the reactants. So the reactant will simply just your H2Br2. The product will be just your HBr. Anything that doesn't belong to your reactant or product, it's intermediate. The third step is actually find out the slowest step. So under this case, your reaction rate can be simply written as K times your Br times your H2. Once you see this, you will realize this is your reactant, but Br is not. How you find a way to convert your Br back into your Br2, because Br2 is actually a reactant. So the things we can use is find out the equilibrium relationship between Br and Br2. So from here, you can write your KEQ is going to equals to Br seconds power over your Br2. So you know your Br is simply equals to the square root of your KEQ times square root of Br2, which is KEQ times Br2 1/2 of the power. Replace this guy with this. This will be K times square root of your KEQ times Br2 to 1/2 of power times your H2. And then these two eventually combine and form a final coefficient Kf times your Br2 1/2 of the power times your H2. Then you can show the red law is really proportional to the Br2 to the square and H2 to the first power.